Hello, my name is Luke and welcome to this PyTorch tutorial series. In this video, we're going to finally cover text generation with our sequence-to-sequence model, or LSTMs, that we've been using so far in this section. So we are in section 12. As per usual, all of the code is in my PyTorch GitHub repo, link in the description. If you're new, remember to like and subscribe. Stay tuned for some more advanced videos soon in this series. If you're joining me again, welcome back. If you'll recall, in the previous video, we showed how we can finally introduce text data with tokenizers and vocab into our LSTMs so we can treat them like a sequence, like we did with our time series weather data, and do text classification. We were classifying some articles then. But right at the start of the section, we actually used that time series data to try and predict the next day's weather. So we had previous days, or several days or months of weather data, and we tried to predict the next day's data. What we're going to start to look at now with this video and this notebook here is doing the same thing but with text data. So we have our sequence of tokens from our sentence, and we're now going to try and predict the next token. So next token prediction, and with that we're going to now try and generate some sentences or some news articles that we're going to do here. So that's basically the foundation of a lot of LLMs, large language models. It's just next token prediction. Some are more complicated than that. They add extra steps after that or before that, but at their heart, that's really what a lot of them are doing. So as I mentioned, we're pretty much going to do the same thing we did with that next day weather prediction. We're going to do a many-to-many prediction. We're going to input a token, try and predict the next token, but we're not going to feed back the predictions back in. We're just going to always use the ground truth, and we covered that in those previous videos. So we're going to use that AG news dataset again, but we're not going to use it in quite the same way. If you don't already have it downloaded, you can uncomment out these two lines here. Like I mentioned, it is a data pipe, not a data class or data set. So you need to sort of iterate over it before it actually downloads the dataset. So if you want to get the dataset downloaded easily, you can just do that, but we're not actually going to use that data pipe like we did in the previous video. I've actually created a PyTorch dataset because I wanted to do a little bit of filtering, and this was just the easiest way, I thought. So we're actually going to load that CSV with pandas and play with the actual data a bit. We're going to remove the actual class labels. If you remember, we had the title of the article, the content, and the class label. We were trying to predict the type of article it was: sports, politics, or science, or whatever. But we don't really care about that label, and I'm going to merge the title and content together. As you can see here, we've got the title, and I'm actually going to separate them with a colon, and that's going to be important later on. And I've got the title, and then we're going to have the content, and then we're going to remove the originals, and then we're going to do some filtering, some very basic regex filtering. You could do a lot more. That's because the actual dataset has a lot of random special characters like new line characters, return characters that sort of just show up as strings. It has a lot of other random special characters as well that you could probably also remove. We'll see those in the vocab as well, but I've just done a very basic filtering here. So once we have that dataset class, we can create an instance of it for our training and testing. Now, the other thing we're doing different is that we're not going to use that very basic word tokenizer. We're going to use something a bit more advanced. Remember in the previous video, we used that basic PyTorch tokenizer, just, separating the words or word-like objects where there were spaces. Instead, we're going to train a SentencePiece tokenizer. So PyTorch actually has a functionality to train a SentencePiece tokenizer model. It is in the text data functional part of PyTorch. And a lot of this is actually just around the SentencePiece model. And basically what this is going to do is kind of train a model to segment sentences with the least number of tokens possible. So it will segment our entire data set with the least number of tokens possible, and we actually provide the size of the vocab we want. So we're going to stick with the default 20,000. We had 50,000 before. We're going to try and get it to only tokenize with 20,000 tokens, and we're going to use the default as well, unigram. This means we're going to try and use whole words or part of words. You see, we can also do the characters or the words as well, whole words, but we're going to use the unigram. So we'll also segment some words that have common endings like ing, building, climbing. Instead of having separate word for build and building. We'll have one for build and ing. I think building is a whole token, but I think create and creating, there's not separate tokens for that, but we'll see that in a second. So we actually need to train this model, and to do that, we need to provide it with a data set. So that's what I'm doing here. I'm just loading the training CSV. You could just pass it the train CSV directly, but again, I'm trying to filter out some things and remove like the label and filter out some things. I'm also making it all lowercase as well. So you need to also separate each sentence by a line, a new line as well. But I'm making it all lowercase so that you don't have separate tokens for things like build with a capital B or a lowercase b. We want them to be separate. And then to actually train the model and the vocab, you just need to pass it the actual text file or CSV, vocab size, and a model prefix. So this will actually save your SentencePiece tokenizer model and a vocab. And this is just the prefix of that. So it can be whatever you want. So that'll actually take a few minutes to train. Our dataset isn't too large, so it doesn't take too long. With a much larger dataset, it will actually take quite a bit longer. But once you've got that, it'll be saved in the same directory. And then you can, if you wanted to, load the tokenizer like this, but we're going to do it a bit differently. But just for the sake of showing you, we have our tokenizer here. This will actually not directly tokenize our sentence. It will return a generator over the tokens, just a slight difference. So it will return basically a thing we can loop over. So if I have some sentence here, I am creating, because I think creating does actually exist as create and ing, just as an example. And then we're going to print the tokens. So I am create ing. There you go. If you just, so this just returns a generator. Just wanted to show you that. So the generator, you need to loop over it to get the actual individual tokens like that. So there we go. I am creating, I am create, the ing, right? And that's an example there. Like I said, it also saves the vocab. So what the actual words or parts of words, sentence pieces are in English. And we're just going to use the build from vocab iterator as well to actually create our vocab object. And we need to provide it with an iterator. So I've just loading the vocab, reading line by line. And we're just removing, if you actually go into the vocab file, you can see that it has, I think, the frequencies of the words as well. Too sure. So I don't want those. I just want the actual characters. That's why I'm indexing here. And you also need to return that as a list. Some small things. Just like before, we're also going to add the special characters. Our pads are start of sentence, end of sentence, and unknowns as well. So how we're actually going to use this tokenizer is with PyTorch's SentencePiece tokenizer transform. So we'll include this into our dataset or data transform, unlike before in the previous video where we had this as like a separate action to our actual transform. We can now incorporate this transform into our transform here. I've just created this separately, even though I'm not actually using it, but just showing you here. I've also created an additional transform. You can create your own dataset transforms. I don't know if we've looked into that too much, but it's basically just an n.dot module, and the call function here is just how you actually do the transform. This is just to randomly drop some of the input tokens or just replace them with pad, in fact. I won't go into that too much. This is probably more useful than the sentence classifier from before because it does overfit a bit. But here we're just trying to drop some of those input tokens or replace them with a pad just so it doesn't overfit too much. You can just add this directly into your transforms, but I'm actually doing this as a separate thing as well. But just because I didn't want it to do it during testing. But don't worry too much about that. Okay, so here I've actually created two transforms. One I've called train transform and one called gen transform. So here's my SentencePiece tokenizer. It's now a part of my transform. I also have the vocab transform. So the SentencePiece tokenizer will tokenize, and then we need to convert those into integers, and we'll add our start and end in padding just like before. max length as well, we are only going to, we're going to truncate at max 64 tokens. Now the second transform I've got here called gen transform. The reason I've got this is because later on when we want to do inference on our model, what we're going to do is we're going to take our sentence and we want to transform it into tokens, but I don't want it to add an end. I don't want to firstly truncate, I don't want to truncate, and I don't want it to add an end of line token. You could use the same transform and just remove that, but I've just created a separate transform here, but we'll go into that in a bit more detail later on. But for now, our training transform. So we're going to create our data loader from that data set as well. And here's just an example of some data from our training set. So let's get a bit of a shorter one, easy to look at. So here's our actual sentence. Note here that we've got that colon separating our title of our article and also the content here. And you can see our actual tokens. We've got our start of sentence, and then we've got our tokens from the tokenizer. You can see that 237 has actually been broken up into 23 and 7. So the number 7 obviously occurs enough that it gets its own token. 23 gets its own token as well. So same with 3 and 1, 31, 3 and 1 probably occur enough to get its own token. You can see that visiting has been split into visit and ing. There's probably some other examples as well. And we've got our unknowns in there as well. And then we have our end of sentence and then our padding. This is a batch, so obviously there's another sentence in the batch that's longer than this one. And just a quick here, we can actually convert from our tokens back into an actual sentence, or the actual, from the integers into the actual tokens with the vocab lookup tokens. So you can provide an array of tokens here, and then we can go use the vocab lookup, and we're just joining them with nothing, because the spaces are also included in there. The spaces are kind of like this thick underscore here. So we can convert them back into the sentence. You can see the start of sentence here, and we've got our tokens here, but the unknown will be unknown still, an unknown. Okay, so hopefully that's clear. So that's how we're going to go back when we want to generate our sentence into an actual readable thing. Okay, so our LSTM is going to be pretty similar to the text generator or text classifier, except instead of 4 classes, we're going to have a class for every single token. So not only now do we have this big embedding where we have a vector, you see size 256 for every one of those 20,000 or 20,003, or because we have the special ones, but we now have an output that's going to be hidden size divided by 2 by 20,000. So a lot of parameters now, because we're doing a classification. All we're doing is classification, just like a text classification, except now we have a single output class for every single token in our vocab. And so that's how we're going to do the actual prediction. We've got our embedding. I've got an MLP in here as well. We probably don't really need this before our LSTM, but I find it just trains a bit faster with that. Because we're trying to learn our embeddings from scratch, from random, it can take a little while for that. The performance isn't as good. We'll look into the future of how you can pre-train your embeddings and freeze them during the actual training of your model. But for now, we're learning them from scratch, and so this just kind of just helps it learn a bit faster, or learn at the output of the MLP and embedding that means something to the LSTM, right? Because if we initialize it with Gaussian random noise, it can take a long time for that actually to move to something useful. But we have our LSTM. We're going to have a number of layers. We're going to have 2 layers here. We're going to add dropout. So there's an option for dropout in our LSTM, again, to stop overfitting. And then we have this little MLP on the output with dropout as well. That's actually going to do the classification. So here in our forward pass, we have our input sequence, as well as the initialization for our hidden in memory. Input sequence, which is going to be integers. Like before, we get the vector embeddings, put them through our MLP, through our LSTM. That will do the whole sequence processing, and then we're going to get an output per element in that sequence for all elements in the batch, and then we'll get the output for each one in that sequence, and then we'll do the classification. So in the text classification, we only took the very last element and then classified from that, right? But it would backpropagate through time in that many to one but we're going to do many to many and perform a classification after every step, again, predicting the next step token. Hopefully that makes sense. Just defining my device. For the text generation, I found, and in general it's true, that that hidden memory, the hidden representation and the memory cell representation, you want that to be reasonably large so it can pass a lot of the information along. Without text classification, you don't need to pass that much information along to the next step to try and work out what article it is. But if you're trying to generate the next token, you might need to remember pretty far back in the sequence in order to work out what the next token should be. So for coherent long sentences, you normally need to make that quite long for an LSTM. We have our atom optimizer, and we are using cross entropy loss. Like I said, we are just doing classification. And I've also created that token drop transform. So it's going to randomly drop some of the input tokens every now and then. The actual training loop is very similar to what we saw before with the next day prediction, where we weren't feeding back the prediction back in. So all we need to do is define the inputs. So we have our actual sentence with the tokens, and then we need to define the input as just all of the tokens, subtract the last one, and then the output is just that sort of shifted along, so dropping the first one and keeping the last one. So we take that sentence and we sort of shift it along so that we can, so it sort of lines up to predict the next token, right? Hopefully that makes sense. We initialize our memory buffers, and then we're just going to put everything into our model, and it will, like I said, that LSTM block will do that sequential pass, and we'll get an input, an output for every step. So we'll get our prediction. The shape of this prediction is going to be batch size by length by output, like the number of tokens. For the cross entropy loss, it needs to be batch size by number of classes by like the number of the sequence length. Right, that second channel, or channel index 1, needs to be the thing that we're softmaxing over. That's just how this cross entropy loss function is defined. So we need to transpose the last 2 dimensions and sort of just rotate that matrix to do the classification, right? So that it's number of classes and then number of output elements, right? So we're doing a classification for every output in our sequence. And we're just classifying with the actual output tokens, right? Again, they're just indices of the actual vocab. Okay. One last thing, I'm also just logging the entropy of the distribution. So here we have that prediction. I'm just taking the prediction distribution, and I'm probably should transpose that as well. But I'm basically just going to try and work out what the entropy of the probability distribution is, and we can see that it actually reduces over time. But I've actually already trained this and saved the model because it does take a little while. It takes about 2 hours to train for 20 epochs. So I've already gone ahead and pre-trained that, but you'll see it does decrease, but it does take quite a long time to decrease, and it's very noisy, because that's the thing with this sentence prediction. Unlike classification, we don't actually expect our model to get a very high accuracy, because, you know, if I give you the initial prompt, hello, my name, you're not going to get the next token prediction 100% accurate just by the initial prompt, hello, my name is, right? You're not going to be able to predict what the actual next token is going to be. But what you are going to be able to do is maybe produce a distribution over the probable next token. Right, so that's what we're hoping to see here, is a distribution over the tokens, with some tokens being more probable and some being less probable. But our actual model, if we try to calculate the accuracy, it's going to be very low. But we don't actually expect our model to be able to have a very high accuracy at predicting the next token. All we want is that distribution to make sense, to be able to make sense. So you can actually train your model for quite a long time, and the accuracy won't actually go up, or the loss won't go down that much, but it is still actually improving. Okay, but enough of that. Let's actually have a look at some of the results. So I trained this, like I said, for the 20 epochs. and loaded it again, just very basically. So now we want to generate some text with our trained model. What do we do? Well, what I'm actually going to do is we're going to use the fact from before that I had the title and the content of the article sort of stuck together, separated by that colon. And what I'm going to do is I'm going to kind of try to coax my model to generate the context of an article from a title by, inputting some title and then having that colon there, and then the model should go, oh, this is the title. I have to now predict what the actual content of the article is. So I'll just use an example here. We'll, in a second, actually use some examples from the actual test set. But for now, let's just use one that we've made up. So the next big thing from Google, and then I've got that colon there. So here's my prompt, next big thing from Google. We've got the tokens and the actual vocab. So that's not relevant now. Okay, so how do we actually generate our text? Well, what we're going to do is, similar to what we've seen before, initialize our memory buffers, and I'm going to input that token, or that set of tokens. So it's going to be more than one token at the start. Right, so look at our shape. It's going to be 1 by 8, so batch size 1, sequence of 8. So again, that LSTM will do that sequence sequentially, and we'll actually get an output here after that first step of 8 outputs trying to predict the next token. But we don't care about all the first ones, we're going to care about the last one. And so once we get our prediction of the last one, what we're going to do is one of two things. What we could do is, because again, we have those class probabilities, what we could do is just take the argmax, be greedy and take the token that has the highest probability or the highest likelihood according to the model, and that will be our token. Or what we can do is sample from that distribution, right? If you only take the argmax, your sentence can be a bit rigid, and sometimes it does repeat itself over and over and over again, but it also means that from the same prompt, you'll only ever get one response. If you want it to be a bit more flexible and want multiple responses from the same prompt, what we'll do instead is sample from the distribution. So that's what I'm doing here. I've got my output of my model, indexing the last one, and those are my logits, so I don't have to do softmax for this categorical distribution. Side note, the categorical distribution, if you haven't seen it, just comes from the Torch distributions. Again, that's just a multivariate categorical distribution. Will select one of the tokens from our probabilities. Note here as well that I'm dividing it by a variable called temp. You may have heard of temperature before when we're sampling. This basically controls or sort of skews our distribution to basically make it more or less random. So we have this distribution from the output of our model. We can actually make it more greedy or less greedy by changing this temperature. If we decrease the temperature, right, and divide our logits by a very small number, logits will become quite large. When you do a softmax, the distribution becomes more concentrated towards the largest one. So if you divide the logits by a small number, we get a larger logits. Softmax, that probability becomes concentrated towards the largest probabilities. And if we relax that, then it becomes more like the random distribution. If you leave the distribution as is, it does tend to be a bit too random, so you might want to drop the temperature a bit. If you increased it past 1, you would have an even more random distribution. The distribution becomes flatter, higher entropy, more random. Okay, so let's now run this. Sorry, another thing. Once we have that distribution, we can sample it, and then we put it back in to get the next token, and we go on and go on and go on. I've got it going for a max of 100 tokens, or we're going to break when the token is equal to token index 2, which is the end of sentence token. So we can actually expect our model to predict an end of sentence token when it's done. Right, whenever it's done, it'll produce this token, and we can break early if that happens, which it usually does. So let's generate our sentence. Okay, so the next big thing from Google, and we have our generated here, text here. Google is adding a new search engine that has been the most important to the company website to make it easier for Google. The search engine is the first step in the search engine. So not quite completely coherent sentence, but it is able to string the words together in a way that does make sense. The sentence as a whole doesn't really make sense, we have been able to generate some text from a prompt. I'll just show you what happens if I don't include that colon there. It adds it straight back in. You can see the first token here. It adds it straight back in. So maybe if we make this a bit shorter, it obviously thought, okay, that's the title. It's done. There we go. It's added thing and colon. So the next big thing colon. The Red Sox have yet to wait for another time to make it available to the Yankees. So it's strung a sentence together. Doesn't really mean too much. But, yeah, so you can actually prompt it that way to try and generate an article. So let's have a look at some actual ones from the test set. So here we go, sounding off to deep space. Let's have a look at the original article. To explore deeper and drive maximum efficiencies, there you go, from sound waves. So you can see it's like a science article, or a very short science article there. Let's see what our model does with that initial title. The world's biggest computer maker is using its first ever spaceflight to the United States, but the company is turning the way to an end. Okay, so it's worked out that it's kind of sciencey and it's related space to space flight. So it has understood the title a little bit and has generated some text that is generally in the same theme of the title. So we can do that again, randomly sample another one, find a good one. So Australia, there you go, it's relevant to me. Australia living beyond its means. We're consuming 20% more natural resources than the planet can produce. Okay, let's see what our LLM does, or our model does. So you can see we have these, just a side note again, these random hashtag 39s actually appear in the dataset quite a lot, 39, 38s. I'm not entirely sure what they are. They may be a special character or a random character. Again, this is what happens when you randomly scrape the internet. So whoever's done this hasn't filtered this at all. So adding this as well as something you might want to filter out from the dataset might be a good idea. So Australia living beyond its means. So here we go. Australia's Prime Minister John Howard has warned of a, quote, positive quote of the country, terrorism and threat to halt his war in Iraq. So it's worked out that John Howard was a Prime Minister of Australia, so it has worked that out as well. Okay, so here we think this is a sports-related article. So we can see what it says for that one. By the University of Florida. I don't know much about US sports, but there you go. You can play a lot around with this quite a lot, and put in your own prompts and whatnot once you've trained your model. The last thing I just want to have a look at is actually having a look at the distribution, just as an example. So I've shortened the number of tokens that it's going to give me to cut off before it gives me the end of sentence token. So we're going to have a look at the distribution here. So the Florida Gators have been happy to learn how to. Next token is our distribution. So you can see we've got a few examples here. If I now change the temp, I might just change it here. If I change this temp to something a bit higher, you'll see that the distribution is a bit more noisy now. I make it very small. You can see we only got one really big peak. That's probably too small. So you can see how if we divide the logits by a small number after the soft max, it does skew the distribution towards that highest probability there. So that's what we're seeing. Right. So if it's too random, we get something that sounds a bit gibberish. So if I set that to 0.9, let's try again with something else. It's done all right. Internet Management System has introduced novel enterprise. Let's try again. Yeah, a bit shorter for some reason. Didn't like that one too much. Let's try another one. Yeah. Very short articles now for some reason. There's more of a chance, I think, of it hitting the... Oh, sorry. I didn't increase it. Back up. One more time. There we go. There we go. Virgin launches online music service. Virgin launched a commercial and music service that being launched, built by Napster Online. The Napster is now the latest move or launched the original, which is launched Intel and Sony. So it liked launched for some reason. So it's repeating that over and over again. But, you know, Napster was a music streaming service or way to download music way back. Intel and Sony. So vaguely text related as well. So it's kind of worked it out. Okay, so I won't go into it too much. Hopefully that was interesting. Hopefully you can see now how we can use all the things we've learned and build a text generative model. That's really all we've done here, taking what we've already seen and putting it together in a new way. And the next video, we're going to see a more advanced way of doing a similar thing with a larger data set. So I'll hopefully see you then.